Welcome to the second lecture of the Global Homotopy Theory class. In the previous lecture I gave a brief review of certain basic notions. In particular I reviewed the category of orthogonal spectra. I reviewed what orthogonal G-spectra are, with a special emphasis on the case where G is a compact Lie group. That will be the case we mostly care about. And I reviewed the equivariant homotopy groups pi k G of an orthogonal G-spectrum X. Today I want to make a few more comments on the equivariant homotopy theory for one particular Lie group at a time, and then later I will turn to global aspects of the theory. Let me introduce the most important kind of equivalence that we want to consider when studying orthogonal G-spectra. So here's a basic definition. So let G be a compact Lie group. Then we'll have a morphism of orthogonal G-spectra. So let f from x to y be a morphism of orthogonal G-spectra. And then we'll define what a pi star isomorphism is, and I will underline the pi star isomorphism in this context, and you'll see why. Then f is a pi star underlined isomorphism if for all closed subgroups h of G and all integers k and z, the induced map on H equivariant homotopy groups pi k h of f going from pi k h of x to pi k h of y is an isomorphism. So this is an important definition, and a couple of comments are in order here. So first of all, why closed subgroups h of G? Well, another fact that is very useful to keep always in the mind is that a subgroup of a Lie group is itself has the structure of a Lie group if and only if it's closed in the topology that's given. And also, as I already mentioned last time, if a topological group has the structure of a Lie group, then it has a unique such structure. So this is why we would typically consider closed subgroups. These are exactly the subgroups which are compact Lie groups in their own right with a unique such structure. Another thing which I will in the future just do without further commenting. So I had originally defined G-equivariant homotopy groups for orthogonal G-spectra. So now I'm taking H-equivariant homotopy groups, so I should have an orthogonal H-spectrum. And that simply I get by restricting the G action to the closed subgroup H. That gives me an orthogonal H-spectrum. And then these groups are of course formed with respect to the chosen complete H universe. If I just had a single G and a couple and its subgroups H, then I could pick the complete universe for G once and for all, and then take the restrictions to the closed subgroups as my chosen complete universes for H. This would work, because if you restrict a complete G universe to an H universe, it's going to be complete. So this is ultimately a consequence of the Peter-Weil theorem, which in particular implies that every H representation can be embedded in the underlying H representation of a G representation. On the other hand, we will soon want to do things globally, and then there is no good way of choosing a complete universe for all the groups G which are sort of closed underpassing to subgroups anyhow. So at that point we would have to confront the fact that this is a choice, the complete universe, and we might as well do this here. The last comment I want to make here is you might have heard about the notion of an ROG graded equivariant homotopy group. So if you're really careful, you can snug in representations where I have the k positive or negative. You could put in, instead of an RK with trivial actions, you can put in a representation in two possible slots. And this way grade by pairs of representations, or if you're really careful, you can actually grade by the representation ring, ROG, although that involves some sort of subtleties. You might wonder why I'm not asking for isomorphisms on ROG graded homotopy groups, however they are defined. Well, the point is, if I just ask on isomorphisms of Z-graded homotopy groups, but I ask for that for all closed subgroups H of G, This will imply that also for all closed subgroups we'll have isomorphisms on the ROG-graded homotopic groups. So it's actually not necessary in order to define the equivalences to talk about ROG grading, and so we won't, because we want to keep things simple. Great, so some more comments about this notion of pi star isomorphism or pi star underlined isomorphism. So here's a bunch of facts that I will write down, and then again you will see some slides with the precise references. So the first fact is that the pi star underlined isomorphisms, pi star isomorphisms are part of stable model structures on the category of orthogonal G-spectra, for which I used this notation. And in fact, there's actually a variety of such stable model structures available, all with the same equivalences, these pi star isomorphisms. So in historical order, the first one was introduced by Mandel May in their MSS memoirs. Then a different stable model structure with these equivalences was introduced by Martin Stolz in his PhD thesis, and yet another one was introduced, at least for finite groups, by Hill, Hopkins, and Ravenel in their appendix on the paper of the covariant variant 1 problem. So you see all the references down here. A consequence of having a stable model structure is that if we localize orthogonal G-spectra at the pi star underlined isomorphisms, so and let me be precise what I mean the quasi-categorical localization of the category of orthogonal G-spectra, the one category of orthogonal G-spectra at the class of pi star underlined isomorphisms is a complete and co-complete stable infinity category. So if you prefer to phrase things in terms of infinity categories rather than model categories, that's perfectly fine, and this is a standard procedure that you can find in the writings of Jacob Lurie, for example. I personally think of a model category structure as a presentation of a homotopy theory, or as a presentation of a complete and co-complete infinity category. And also, if the model category structure is stable, which means that on the level of homotopy category, suspension and loop are inverse, and it's pointed, of course, then the associated infinity category will be stable. And another fact in this particular example is that this is actually a presentable stable infinity category, which is not a consequence just of the stable model structure, but it's a fact here. I will briefly come back to this in a second. So another consequence of this, either of the stable model structure or of the stable infinity category, is that the homotopic category, the G-equivariant stable homotopic category, so here, let me introduce a notation. I write mathcal as H sub G for this, and this is by definition the localization, but now in the category theoretical sense, of the one category of orthogonal spectra at the class of pi star isomorphisms. So this is naturally a triangulated category. So of course you know that a triangulated category is not a property, it's extra structure on the category, but this comes naturally from either the model or from the structure of a stable infinity category. So again, I'll give you three possible references in case you don't know how to prove this. So one is to Hovey's book on model categories. Another one is to a research paper of my own where I do this a little bit more generally with stable co-fibration categories as opposed to stable model structures. And there's also a reference to Lurie's higher algebra, where this is done for stable infinity categories, where he proves that you get a triangulated structure on the homotopic category. So triangulated, of course, in particular means, and this is also important, that it's an additive category. So the Hom sets come to us with abelian group structures, such that composition is additive in both variables, and we have finite sums and finite products, and the canonical map is an isomorphism. So there's also another piece of structure that I just want to mention here, and this is that the smash product of orthogonal G-spectra so this derives to the homotopic category, or it descends if you want, and it derives to a symmetric monoidal structure. And it's actually closed, it has internal homes, closed structure on the G-equivariant stable homotopy category. So I think I'm not going to talk a lot about the smash products in this class at all, despite the fact this is one of the original reasons why orthogonal spectra and their cousins symmetric spectra were originally introduced, because they're good models for the non-equivariant stable homotopy category with a nice poinset level smash product. Nevertheless, the kind of things I want to concentrate on will not really involve the smash product very much, so this won't play a particularly important role. Still, it's a good point to mention this here. So you can also summarize this by saying that the triangulated homotopy category actually has the structure of a tensor triangulated category under the derived smash product, where the equivariant sphere spectrum is, of course, the unit. And then one last property about the G-equivariant stable homotopy category, and this is that this triangulated category, SH sub G, is compactly generated by the suspension spectra sigma infinity plus of the homogeneous spaces G mod H for all closed subgroups H of G. So in fact, I'm not sure I know a reference where this is formulated exactly in this way, but of course there are lots of places where you can essentially find this. So this is a direct consequence of the fact that these orthogonal G-spectra, the suspension spectra of G mod H, that this represents in the homotopy category, it represents the functor of taking H-equivariant homotopy groups. Because H-equivariant homotopy groups take wedges to sums, this means that this object is compact in the sense of triangulated categories in this triangulated homotopy category. And because by design an object is zero in the G-equivariant stable homotopy category if and only if all the H-equivariant homotopy groups vanish, this directly means the representability property means that these objects generate the triangulated category. So here's also a reference to the global homotopy theory book for the fact that the suspension spectrum of G mod H represents the functor pi 0 H equivariant. This ends my brief review of equivariant homotopy theory for a particular compact Lie group. We would certainly have to go back to that frequently as we proceed and prove things in the global context, because a lot of things basically refer to equivariant homotopy theory for one group at a time. Nevertheless, I now want to turn to global aspects, and I want to start explaining how orthogonal spectra model global stable homotopy types. As I mentioned in the introduction, a stable global homotopy type is supposed to be some kind of collection or compatible system of equivariant stable homotopy types, one for every compact Lie group. And the question is, how do you make this precise, in particular this compatibility? You could contemplate actually taking a G spectrum for every G and lots of data that you include with it that relate the various restrictions, but somehow a little bit of a miracle happens, and the category of orthogonal spectra, where we don't have any additional group acting on them, by some sort of miracle that I still don't fully understand, even having thought about this for quite some time, just the category of orthogonal spectra with no additional group actions turns out to be a very nice model for this compatibility and this global approach to it. So this is what I want to explain now. At first sight, it should be surprising that objects with no action can actually model objects with actions of all groups, and it does take some time to appreciate and understand how and why this actually works with orthogonal spectra. Another point is that the orthogonal groups are built into the definition of an orthogonal spectrum, and you might know that every compact Lie group can be embedded as a closed subgroup into an orthogonal group, or equivalently, every compact Lie group admits a faithful finite dimensional representation. This is ultimately a consequence of the Peter-Weil theorem. So that's sort of explaining the secret to some extent, because by the time we say orthogonal spectrum, we have secretly already built in all the compact Lie groups, at least behind the scenes. This is also explaining why it's important to work with orthogonal spectra. So you cannot model, at least I wouldn't know how to model, global homotopy theory with some kind of sequential spectra, which are just sequence of spaces connected by structure maps. If you only cared about finite groups and not compact Lie groups in general, then there is an alternative by using symmetric spectra. So there is a global model structure on the Harvey-Shipley-Smith category of symmetric spectra that models global stable homotopy theory at finite groups. This is due to Markus Hausmann, and you can find it in his paper. Okay, the key thing is how we associate to an orthogonal spectrum an orthogonal G-spectrum, and we do this in the most trivial way. Nevertheless, this is, while it is trivial, it is so important that I want to highlight it as a definition. So let X be an orthogonal spectrum. And G a compact Lie group. Then I want to say what the underlying G-spectrum of X is. The underlying G-spectrum X sub G of X is the orthogonal G-spectrum, so is X with trivial G action. So this is a long definition, or reasonably long definition for a very simple construction. We just give it the trivial action, and the surprise is that this leads to non-trivial mathematics. So in practice, I will often not write down the sub G when I'm doing this to save some notation and make things easier to write down. So I will often just write X again and have secretly endowed it with a trivial G action. And in particular, I will do this when defining homotopy groups. So if X is an orthogonal spectrum with no additional action of G, I will write pi k G of X for pi k G of X sub G. In other words, I will endow X with a trivial action. And the reason that something interesting comes out is, so you should remember, when we defined equivalent stable homotopy groups, we were evaluating at non-trivial G representations. And despite the fact that the group acts trivially on X, it still acts non-trivially on the representations. And this is fed into the definition of equivalent stable homotopy groups through the functoriality, because the value of X at V has an action of the orthogonal group, and if G acts through a homomorphism to the orthogonal group, this gives non-trivial G spaces. So even if X is trivial G action, this can be very interesting groups, and that's what we will study in quite some detail here. Okay, so now I can define the most important notion when it comes to the category of orthogonal spectra from a global perspective, and this is the notion of global equivalences. So a morphism f from X to Y of orthogonal spectra is a global equivalence if for all compact Lie groups G in all integers K the map, which is always a homomorphism over given groups from pi k G f, pi k G x to pi k G of Y in this sense up here, so we use the trivial action, is an isomorphism. Okay, again, I would like to make a bunch of comments before going on. The first comment is that you could vary the class of groups, so this is one parameter that you can build into the theory. Instead of asking this for all compact Lie groups, you could first fix some class of compact Lie groups and then ask this for all G in that class. So particularly interesting classes would be the class of all finite groups, but maybe you also want the class of all abelian compact Lie groups, and there are all sorts of other possibilities. There's a few points in the theory where things work more smoothly if you assume some closure properties for this class, that's such that it's closed under passage to closed subgroups and quotients, and then the model structures and so on work out smoothly, but that's probably not even relevant there. In particular, you can include the class of all trivial compact Lie groups, so all compact Lie groups with a single element, and then you would just, the whole theory would specialize to non-equivariant stable homotopy theory. So I'm now mentioning this at the outset, that there is a version of global homotopy theory relative to something that I call the global family of compact Lie groups, which is just a class of compact Lie groups with certain closure properties. And pretty much everything works exactly the same way or has obvious analogs when you fix a class of compact Lie groups. I will usually do it for the biggest interesting class that I can think of, which is all compact Lie groups, but sometimes we want to have this modification available. Good, so now we have this notion of equivalences, and as we did with the pi star isomorphisms of orthogonal G-spectra, we might want to localize them in some sense. So let's first do the brutal one categorical localization, and this defines the global stable homotopy category. So the global stable homotopy category so now I will use the symbol mathcal GH for this. This is again a localization of the category of orthogonal spectra, but now it's the one categorical localization at the global equivalences. So this is a definition we can make. Let's assume that this exists, and then it's unique up to preferred isomorphism of categories. But for this to be useful, we need a little bit of more information. And something that I'll talk about later is that this supports a global model structure. So just as the pi star isomorphisms of orthogonal G-spectra are part of one or actually several model structures, these global equivalences are part of what I call the global model structure, something I will talk about later. And in particular, this has the same kind of consequences that I pointed out when I talked about orthogonal G-spectra. This model structure will be stable, so one consequence is that this homotopy category comes naturally with a triangulated structure. Also, because it's a model structure, we could take the quasi-categorical localization and we would arrive at a stable infinity category, which is complete and co-complete. Something I will also talk about later is that the triangulated category has a specific set of compact generators. It's compactly generated. The global stable homotopy category is compactly generated by objects that are called, this is unreduced suspension spectra of the global classifying spaces of the compact Lie groups. I will explain this in quite some detail later. These are very important objects. These are the basic building blocks of global homotopy theory. Heuristically, you can think of this as that there exists some universal compact Lie group, which doesn't actually exist, but which is contractible, and this is really the universal one modulo G. So in some sense, this is a close analog of the fact that the G-equivariant stable homotopy category is generated by the suspension spectra of the G mod H's. So these are like the universal groups modulo G, but this is just heuristic, so this is not really how we're going to make it precise. Now I would like to talk for quite some time about the structure that the equivariant homotopy groups of a global stable homotopy type have. So in other words, the equivariant homotopy groups of an orthogonal spectrum. I call this kind of structure a global functor because it is a global kind of Mackey functor, but it's a very specific global kind of Mackey functor. And it's the one that comes up in this context, so I'm going to use this slightly shorter name, global functor, as opposed to global Mackey functor. So this is a little bit of an analog to the fact that for a finite group, the equivariant homotopy groups of an orthogonal G-spectrum for G and all its subgroups together have the structure of a Mackey functor in the sense of algebra and representation theory. So here the situation will be a little bit different in that we don't just have one group and its subgroups, we have all compact Lie groups. And also we really have the positive dimensional compact Lie groups in the picture, which is a little bit extra twist to the story that's not so often considered in purely algebraic contexts. So the structure of a global functor that we'll see on the equivalent homotopy groups is a little bit the pi0 or the homotopy group shadow of this compatibility that is behind the motivation for global stable homotopy types. You know, they're supposed to be compatible systems of equivalent homotopy types. And the global functor sees this system and the compatibility on the level of equivalent homotopy groups in some fixed dimension. The structure on the equivalent homotopy groups will have two ingredients. So one will be restriction maps, which can also be broken up into restrictions to subgroups and restrictions along epimorphisms, or also called inflations. They are of a somewhat different flavor from transfer maps, which are also important, and I will discuss these two kinds of structures separately. In a sense, the restriction maps are more easy to define, and I will do this, but before I get to the definition of restriction maps, I have to go back to one thing about equivalent homotopy groups for a fixed compact Lie group. Namely, suppose we're in the following situation, so let G be a compact Lie group. X an orthogonal G-spectrum. And then we have a G map, F, from S, V to X of V, a G map for some G representation V. So let me one more time remind you of some conventions, and then, in the future suppress this. G representations are finite dimensional orthogonal representations, and the G map, of course, means it has to be continuous and base point preserving and equivariant clearly. That's what it means. All right. So now we would like such a map to represent an element in the zeroth G equivariant stable homotopy group, and this is what I want to explain now. So this will define class that I will note by pointy brackets F in the zeroth G equivariant homotopy group of X. On the face of it, we can't quite do this because these elements are represented by maps of this kind, but V has to be a finite dimensional sub-representation of the chosen complete universe. And on the face of it, it's not so clear. Of course, we can embed V into the complete universe, but you have to check that something is well defined, and I want to explain briefly how this goes. So the issue is that we would like to have the flexibility that such maps define equivalent homotopy elements, even if V is not properly contained strictly a sub-representation of the chosen complete universe. And here's how this goes. So we choose a G-equivariant linear isometric embedding. I call little j from V into the chosen complete universe, and it was the defining property of a complete universe that this exists. It's of course far from being unique, but it exists. And then we set V prime to be the image of this embedding. And then J is in particular an equivariant isometry onto its image. So we can now form this composite. I can go from S V prime via J, or rather in this direction it's going to be J inverse to V, and then I go via the map F to X of V, and then I apply X to the isometry J, considered as a map onto the image. And now this composite is a G-equivariant map, which exactly is of the right form to represent an element in pi0G, because V prime is a finite dimensional sub-representation of the complete universe. So this class represents pointed brackets F. Of course, there's something that is not completely obvious that you have to check, because this embedding is far from unique, and you have to check that the class that comes out here doesn't depend on the choice of embedding. And this in some sense ultimately comes from the fact, although the technical proof is a little bit different, but it ultimately comes from the fact that the space of linear isometric embeddings of V into the complete universe is actually contractible. So let me just record this, and then I'll give you precise references on a slide in the video. So the class is independent of the choice of embedding. The class independent of the choice of embedding J, and it does not change if we stabilize F. And it does not change if we stabilize F by another G representation. So the stabilization procedure is something I've briefly discussed in the last lecture. I denoted it with this diamond sign. You can stabilize from the left or from the right with a representation. And you can do this when V and also W are not necessarily subrepresentations of the complete universe. And you know, this class also depends only on the stabilization, not on the argument. So here's a reference. All right, so then I'll clean the blackboard one more time, and afterwards we'll talk about restriction homomorphisms. I will now define the restriction homomorphisms on equivariant homotopy groups. But before I can do that, I have to talk about restriction functors. And let me do that in a slightly more general context. So now we consider two compact Lie groups, G and K. And we consider a continuous functor between the respective categories of based equivariant spaces, F from Gt star, so this was the category of G-equivariant topological spaces equipped with a G-fixed space point, to K T star. Here a continuous based functor. And this functor induces another functor on the respective categories of equivariant orthogonal spectra, which I just write F circle blank because it's given by postcomposition with F. It goes from the category of orthogonal G-spectra to the category of orthogonal H-spectra. And this is simply given by sending an orthogonal spectrum X, orthogonal G, spectrum X, through the composite, as the notation indicates. So here it comes out quite handy that I had defined an orthogonal G-spectrum simply as a continuous based functor from this indexing category O to the category of based G-spaces. So here's another continuous functor, I can just compose them. I get a continuous based functor from O to K spaces, so that's an orthogonal K spectrum. The construction is extremely simple on the point set level, on the one category level. Of course, in practice, it can often be very difficult to understand what the homotopical behavior of this is. You know, does this functor preserve pi star isomorphisms? If not, can you derive it from the left, from the right, or something like this? This may all be very complicated, but on the point set level, it's a very simple construction. We've already seen two instances of this at the end of the last lecture. So two examples are the functors smashing with S1 and loops. We continue this as self-functors on the category of orthogonal G-spectra. So here G is equal to K. And if we do this to an orthogonal G-spectrum, this means that we level-wise suspend with S1, or we level-wise loop. And these were the suspension and the loop constructions I'd mentioned already in the last lecture, where we had the suspension and the loop isomorphisms. More generally, if A is a based G-space, then we can look at the functor that smashes with A, or the functor that takes based maps out of A. So this is the space of based, not necessarily equivariant maps, with G acting by conjugation. These are two functors again, from based G spaces to based G spaces. So we can do this to an orthogonal G spectrum, and this is what I called object-wise application last time. This gives us more examples of this. Something you might want to convince yourself of, which is relatively straightforward. If you have two functors and the data of an adjunction on the level of based equivariant spaces, then you can promote this to an adjunction at the level of the induced functors on equivariant orthogonal spectrum. Here's another example of this situation. Now G and K can be different, so we look at a continuous homomorphism. let alpha from k to g be a continuous homomorphism, and I explained last time this is automatically smooth in case you wonder. Then it gives rise to restriction functors. So that means we restrict the action along the homomorphism. This is a functor that I will call alpha upper star. It goes from based G spaces to based K spaces. So the functor does not change the underlying topological space and the base point, it just changes which group acts and how it acts. So K acts through this homomorphism. And hence, by this construction, that's clearly a based continuous functor, we get a restriction functor, which I also call alpha upper star from orthogonal G-spectra to orthogonal K-spectra. And as I already mentioned above, this is an extremely simple construction at the point set level. The point set, the unstable functor has both adjoints, so also at the spectrum level this will have adjoints. If alpha is the inclusion of a subgroup, or more generally an injective homomorphism, then pretty much by design alpha upper star will take pi star isomorphisms of G spectra to pi star isomorphisms of K spectra. If alpha has a non-trivial kernel, however, it will not be homotopical, and then you have to invest a little bit more work on studying how it can be derived. It can be derived to a functor on the homotopic category, but that needs a little bit more work then. So one last comment before I erase the blackboard. Suppose we have a G representation. If V is a G representation, then alpha upper star of V is a K representation. So we just also we keep the same underlying inner product space, and we just let K act through the homomorphism. So this is a K representation. And now you may wonder, I can take alpha upper star of an orthogonal G spectrum X. This is now an orthogonal K spectrum, and I can evaluate it at this K representation. And by the way, we have set things up. This is equal and not just isomorphic to alpha upper star of the value of X at V. So this is a base G space, which we can restrict, or we can restrict the spectrum and the representation and then plug in, and these two things are actually equal, because in all the cases we don't change the underlying object, we only change how the groups act, and so this is kind of a convenient formula that comes in handy at several points. As before, I consider a continuous homomorphism alpha from a compactly group K to a compactly group G. And now I also take an orthogonal G spectrum. Let X be an orthogonal G spectrum. And now I can introduce the restriction homomorphism of equivalent homotopy groups. So the restriction homomorphism that I also call alpha upper star by use of notation. This goes from pi 0 G equivariant of X to pi 0 K equivariant of alpha upper star of X. So remember, alpha upper star of X is the orthogonal K spectrum we get by applying the restriction functor level-wise. And this is given by the following recipe: alpha upper star applied to a class that's represented by a G map from SV to XV. V is some G representation. I define this as the class of alpha upper star of F, which on the face of it goes from alpha upper star of SV to alpha upper star of X at V, and it's a K equivalent map. But this is the same in the sense of equal and not just isomorphic to the one-point compactification of the K representation alpha upper star V. This is the same as I just mentioned on the previous blackboard as the orthogonal K spectrum alpha upper star x evaluated at the K representation alpha upper star v. So this makes perfect sense. Well, I guess I should have done something that I'll probably do wrong a bunch of times. You know, even if the original V is a finite dimensional subrepresentation of the complete G universe UG, it's extremely unlikely that when I restrict it, it's going to be a subrepresentation of the chosen K universe. So I have to use this extended way of defining elements in equivariant stable homotopy groups that I talked about 2 blackboards earlier. You know, I have a K equivariant map from the sphere of some K representation to the value of the orthogonal spectrum at the same K representation. So these two representations have to be equal, and that is the case, so it does define an element. Now, of course, there are a bunch of things to check, which are not terribly difficult, and I won't even bother giving any ideas about the proof. You have to check that this is well defined, it's independent of the representative for this class. Then you want to check that it's a homomorphism of abelian groups. That's also not so difficult. And then some facts that I at least want to explicitly mention is that this is basically a contravariant functor. So if we have another homomorphism, if beta from L to K is another continuous homomorphism, then we can consider first alpha upper star and then beta upper star, and we can compare this with alpha composed with beta upper star, and this will be two homomorphisms starting at pi 0 G equivariant of x, and then we'll go to pi 0 G equivariant of, well, the former one would really go to alpha upper star of x, beta upper star of x, but you can quickly convince yourself that this is the same, and of course this is L equivariant, that this is the same as alpha after beta upper star of x, in the sense of really these are equal as orthogonal L spectra, and this is easy to check basically because restriction on the level of equivariant spaces has this associativity property. Also, the identity goes to the identity. I won't even bother to write this down. There's a slightly more interesting feature having to do with inner automorphisms, so let me explain that. So for G and G, we can take a particular we can consider a particular automorphism, namely the inner one. I write CG for this. Let CG from G to G be the inner automorphism. So Cg of gamma, just to fix the notation, is G inverse gamma G. So this is in particular a homomorphism, so it has a restriction map. We need another piece of structure. So L sub G from Cg upper star of x to x, so that this be left multiplication by G. So it's a fun exercise, if in case this is not obvious to you, that if we have an orthogonal G spectrum X and we restrict the action along this inner automorphism, we get another orthogonal G spectrum X. And these two orthogonal G spectra are of course not equal. They have the same underlying spectrum, but they have typically different G actions. Nevertheless, left multiplication by the element G is exactly a homomorphism of orthogonal G spectra from the restricted action to this restricted action. If this is not obvious for you, I recommend you just sit down and briefly check it. And then one of the facts is that the conjugation homomorphism and the homomorphism induced by this morphism are inverse to each other. The two homomorphisms so I have pi 0 G equivariant of x, then I have Cg upper star, the restriction homomorphism along the inner automorphism, this goes to pi 0 G Cg upper star of x. And in this direction, I have left multiplication by G, which is a homomorphism of orthogonal G spectra, and whatever it induces on homotopic groups, these are inverse to each other. So I alert you that, in the global context, we will soon drop this CG upper star, and these will actually be the same orthogonal spectra, but in this context, if X is an orthogonal G spectrum, then you cannot really simplify this, and you have to be careful not to confuse CG upper star of X with X, which, as I said, have the same underlying orthogonal spectra, but typically different actions. So they're different objects, and you may have to make sure that you don't confuse them. So informally speaking, I will sometimes refer to this property as the fact that inner automorphisms act as the identity, and in the context of global stable homotopy types, as I will soon explain, this is sort of literally what it would mean. I'm still considering a continuous homomorphism alpha between two compact Lie groups K and G, but now I want to consider a global homotopy type represented by an orthogonal spectrum. So let X be an orthogonal spectrum with no particular group acting on top of it. We've talked about the underlying G spectrum and the underlying K spectrum, which were both had the triggered actions. And because of that, if you restrict, you get an equality. Alpha upper star of X restricted to G is equal to alpha upper star of K, for the simple reason that on both sides the group K acts trivially. Here it already acted trivially on G, and if you restrict, it's still acting trivially, and here it acts trivially by definition. So alpha becomes a homomorphism. So alpha upper star is now a homomorphism from pi 0 G of X to pi 0 K of X, and I call this again the restriction homomorphism along alpha. So the point now is that there is no alpha upper star here anymore, because there's no need to record it, and there's no ambiguity as what this could mean. Also, for G in G, now the left multiplication map from CG upper star of X, which actually is equal to X, or I mean, I should strictly speaking, I should always write sub G here, to X is the identity. After all, when adding G act trivially, and this exactly means that left multiplication by any element is the identity. So that means we now get the special case that the map CG upper star, which is now homomorphism from pi 0 G equivariant X to itself, is the identity. No, it's inverse to the effect of this map, but that's already the identity, so this must be the identity. So this is now literally saying that if we have a global stable homotopy type, then the restriction homomorphism along an inner automorphism is the identity. Okay, so if we plug all of this together, then we obtain the following consequence. If we look at the collection of the G-equivariant homotopy groups of an orthogonal spectrum X, where G runs over all compact Lie groups, that this collection of groups extends to a functor contravariant functor from a certain category that I'll explain in a second to the category app of abelian groups. I will denote this functor pi 0 underlined of X. So the underlined means that I'm considering the equivariant homotopy groups for all G at once, but with some additional structure on it. And so here rep means the category where the objects are compact Lie groups. Category of compact Lie groups, and continuous and conjugacy classes of continuous homomorphisms. So the fact that we can pass to conjugacy classes is exactly the fact that inner automorphisms are not seen. That's just a translation of what this structure is. So again, I want to make some comments. So the first important comment is that this is not the full structure that we have. The second half of the structure is the transfer maps, but those I will get to in the next lecture. And this is kind of an extensive topic, so I will probably even need more than one lecture to explain the full story that's behind the transfer map. So this is roughly speaking half of the structure that we have of the equivariant stable homotopy groups. Another comment that I want to make is, so if we really look about Lie groups that have positive dimensions so that are not discrete, then it can certainly happen that the space of continuous homomorphisms, considered for example as a subspace of the space of all continuous maps with a function space topology, this space of continuous homomorphisms will no longer in general be discrete. So in particular you can have continuous homomorphisms that are connected by a path of continuous homomorphisms. And you could wonder, shouldn't we somehow have a condition that guarantees that continuous homomorphisms, well this means through homomorphisms, homotopic continuous homomorphisms should induce the same map? Well, it turns out we don't have to require this because that's actually a consequence of a result that ultimately goes back to Montgomery and Zippin. So the original result with the reference here says that in a Lie group, typically non-compact, that roughly speaking it says that nearby compact subgroups are always conjugate. And then a consequence of that, for which I'll also give you two references here, is that in the realm of compact Lie groups, if you have two continuous homomorphisms that are homotopic through homomorphisms, then they're actually already conjugate. So that means I don't have to require that this is constant on homotopic classes of homomorphisms. It already follows from the conjugacy invariance. That's kind of a useful thing to keep in mind. Then I would like to briefly introduce a notation that's going to be convenient. So I will use a standard notation in the special case when we have the inclusion of a subgroup. For a closed subgroup, H of G, I'll write restriction from G to H for the induced map of the inclusion, which is then a map from pi 0 G equivariant to pi 0 H equivariant. And then another piece of terminology that is useful is if alpha is an epimorphism, so surjective continuous homomorphism, then we call the associated restriction map an inflation map. So restriction homomorphism is the general term, and it consists of two subclasses of such things. After all, every continuous homomorphism factors canonically as first the surjection onto its image, and then the inclusion of that image. And because of the contravariant functoriality, this means that an arbitrary restriction homomorphism factors canonically as first the restriction to a subgroup, and then an inflation homomorphism. So the reason for giving these two different names and using different notation is that in a lot of aspects, these two kinds of restriction maps behave very differently. One example will be how they behave with respect to transfers, and I will come back to that later. Another thing that's worth pointing out at this point here is that restrictions to subgroups is a kind of structure that you also have in G-equivariant homotopy theory for one group at a time. So if you're given an orthogonal G-spectrum, then this has G-equivariant homotopy groups, and it has H-equivariant homotopy groups for all the subgroups, and you have the restriction homomorphisms. You also have conjugation homomorphisms, even from H to a conjugate subgroup, induced by conjugation by an element of the ambient group G. And this is, if we leave the transfers aside for the moment, this is the full structure that you have when you have an orthogonal G-spectrum. So you can restrict between the various subgroups as long as they sit inside of each other, and there are conjugation homomorphisms which go from the value at one subgroup to the conjugate subgroup. And of course there are relations and transfers we'll talk about later. So in a global homotopy type, you can already see that this is a very different kind of structure, and it's a much richer structure. So first of all, you have a restriction homomorphism even along surjections. These inflation maps are definitely a truly global phenomenon that have no analog for G-equivariant homotopy group 1G at a time, and they sometimes have drastic consequences. So the presence of these inflation maps is something truly global that is special. So when you recognize a G-equivariant homotopy type as coming from a global homotopy type, this is one of the bonuses that you get. Another consequence of this rep op functor that you get on a global homotopy type is that You know, it can happen that in some compact Lie group G, you have different subgroups, closed subgroups, H and K, that are abstractly isomorphic, but that are not conjugate by an element of the ambient group. If you have a G homotopy type, then there would be no reason why the two values at H and K should be isomorphic. They would be isomorphic if these are conjugate subgroups, but in general there would be no reason. On the other hand, if you come from a global homotopy type, then an arbitrary isomorphism of course induces an isomorphism of equivariant homotopy groups. So that means that the isomorphism class of the group Pi0G only depends on the abstract isomorphism class of G, and not on how this is embedded in some ambient group. This is another consequence. At some later point, once I've discussed the full structure on global functors, I will come back and compare this to Mackey functors for one group at a time, and I will make some more differences more visible here. This is also a good point to answering one question that you might have. So you could ask, if I have a compact Lie group G, is every G homotopy type underlying some global homotopy type? And already at this point, you can see all sorts of obstructions, and this is just completely false. Unless G is the trivial group, where this is the case, as soon as G is a non-trivial group, the forgetful functor from global stable homotopy category to the G-equivariant stable homotopy category, which exists by design pretty much, this functor is very far from being essentially surjective, and it's also typically very far from being either full or phaseful. So it's not at all the case that a G-equivariant homotopy type always arises from a global homotopy type. In contrast, this is something very special, and this is why it can be useful to recognize this. If you have G-equivariant homotopy types coming from a global homotopy type, it's a special situation, you get more structure, you get more relations, and this often buys you something in computations. This is one of the reasons why I'm teaching this class, and I hope to return to specific examples later. Now my time for the second lecture is up, and I would like to close for today, and thank you for your attention.